Carla. Thank you for bringing me here to this beautiful town and this beautiful room, library. That's a very special place. And I have this chance to speak about my favorite subject, which is radiocarbon dating. This is all what I do. I have my email, but maybe mostly I would like to point out this simple webpage address that you can see our facility. As Pavla said, I'm based there. I've been lucky to be there the whole career I spent at ETH, and each time, each visit, I'm always amazed how a wonderful environment we have there. And yes, I underline also the support. And again, I am lucky that Pavla is with me in my office, and we are doing this magic of dating mortars together now. I am not alone for my last 2 years before retirement. So that's really exciting time. Okay, so let's start talking about radiocarbon. I usually have somehow it worked before. Okay, right. Oh, it was too strong. That was too strong. Starting to talk about radiocarbon, this is maybe to archaeologists known things. We can date, use radiocarbon to date objects or even directly archaeological material from the sites that cover 50,000 of human history. This is exactly covered here, but that is the limit of radiocarbon dating method. What a wonderful coincidence, we say, that we are able to really use this method for studies of human history. And I have examples of studies that I've been working over the years, dating charcoal from Zurich, and then some Mediterranean sites from Turkey. You can see here 11,000. It was at my studies were concentrated about this time, younger dryas, which is climatic change that we in Europe was pretty pronounced. Then one of my prominent samples in the lab is remains of Ötzi, the Iceman person that was found on the border between Italy and Austria. And actually, we've done dating early, right after finding, and then over the years, I worked with students. We have some refined new dating there. So, but just to address the group and studies in medieval, you can see here what we do in Zurich. We do a lot of medieval archaeological samples from Zurich, but also from archaeological offices around Zurich in Switzerland. Each canton has own office, and I understand most of this is rescue excavations that they do whenever new buildings are constructed or renewed. And then we get the bones, we get charcoals, not so much textiles in Zurich, in Switzerland, not mostly they would be in museums or collections, but now and then we have everyday objects. And this is not from Zurich, this is an instrument that I dated in collaboration with a French group. But yeah, of course, art objects and written documents is something that we do, yeah, occasionally. It's not everyday bread like bones and charcoal. And last but not least, these medieval buildings that I started to do that maybe 15 years ago. There were the first samples that I was forced to do, really, because the archaeologist, he came with the box of mortar and said, here, you do it. And I had no choice, I had to do it. It was a mix of medieval and Roman samples. Okay, this is actually coming a little bit later in my talk. Usually I would start my talk about this marvel, how I talk about radiocarbon each time. I'm saying this is amazing, you know, because we have this isotope of radiocarbon, and right away you can see the concentration of C14 in comparison with C12 is 10 to minus 12. So how many zeros we have after point. This is what we have to detect in our samples when we measure them. And the wonder of this method is this mix of old carbon that is in us. We are old carbon made of stardust, as Joni Mitchell is singing. If anyone of you knows Joni Mitchell Woodstock song is about old carbon. And we have these three isotopes that we can use for our method. Young radiocarbon, it comes, the picture shows us production of particles. The production is triggered by cosmic rays that come from the universe, very energetic particles hitting the atmosphere and creating, we call them cascades of particles. So that's the origin, and kind of repeating what I said here, the cosmogenic isotopes production and this naturally occurring C14 carbon isotopes that we have, C14 again, highlighting this very, very low concentration. This figure, Swiss cartoon made by my colleague ages ago, with the Swiss cow being a very important heroine here, because we always would think, okay, we have the production of radiocarbon there, what I just explained, very energetic particles, and then neutrons meeting nitrogen in the atmosphere. We have C14 produced, and this will be oxidized, goes to grass, goes to trees, goes to grass, and then the cow will be in equilibrium with this atmosphere. So the cow or the trees, we can say they are recording, and us eating cheese and maybe some beef meat, we have this signal from the atmosphere. But the figure is complicated later. I will show the complications why we have to think of the complex cartoon. Remember this corner with the ocean, that it plays an important role in our later, I spill the beans, calibration is connected to this complicated figure. Okay, and now just to mention how it came about that we can use this wonder of radiocarbon mixed with old carbon. This person, Willy Wiebe, right after the Second World War, he and his students here mentioned as co-authors, they were able to establish the fact that radiocarbon is actually globally distributed and a global marker around the world. So they said, let us check if this radioactive isotope can be used as a clock. That means tool for measurement of radioactivity in historic objects. And they collected various prominent samples, even from Egypt, and some of the famous textiles, and also tree rings that were well dated, and measured radioactivity in those samples. They could show that the starting radioactivity, which they knew what it was around at that time, was declining with the exponential law, which is the radioactivity clock giving us. We have the starting radioactivity, and then we have decay constant of specific decay constant for each isotopes here given as lambda, or we know it as half-life when we talk about the method. And then we have this T that we can tease out of the equation. This will be our age of the material here. Their historic ages told us, or told them back then, that this is working. It's true. We can use this as a method. So that's the start of the method with those assumptions which Libby made. And you can see here, I removed my animation, but actually there is some confusion. There was some confusion and remained as the radiocarbon half-life back then. He started with 5,700 and then switched back to Libby's half-life. And we are stuck with this number here, although nowadays we know that actually physics shows that half-life is a little bit longer. It doesn't matter. Later we will be calibrating our radiocarbon ages anyway, so this confusion will be corrected. So this is just Libby quickly, because I have 60 slides, almost as an archaeologist, as Jerzy told me. That is just to show you how Libby was doing his measurements with the detectors that were smeared with burnt samples. Grams of carbon were required, and then days of counting of particles from the decay were needed to have reasonable precision on measurements. And next slide shows you, I think yesterday I tried to shock the archaeologists in Bern. I don't know if were they shocked. The slide shows you how much people sacrificed for dating. This is the Coptic textile that was burnt. That what is grayish, it's gone. It was used for the radiocarbon dating, which is, you would say, it's crime. Nowadays, we are really, people cry over this small bit, like where my pointer is. And back then they did this huge sampling. And at the same time, I say it's crime, but also how much people wanted to know how old it is. So that is, I don't know if the court will give them some lower punishment. But fortunately, physicists are around, and in 70s, physicists came up with this idea. I will not talk about this too much. The physicists gave us the solution. We can, instead of counting decay particles, we can count atoms of C14. This is why I underline this 10 to minus 12, because this will be, we're counting atoms of C14. And for this, we don't need the days. We can measure maybe for nice precision, we measure for an hour. The one sample will be sitting in the machine for an hour. This is a footprint of the machine. Later, I have a quick slide showing how it goes through the machine when we measure the sample. Small sample of 1 milligram of carbon, that is enough. So let's say 5 milligram of this beautiful textile that we solid. And okay, I just found this is an old slide which illustrates what that means when we are measuring with the machine how big task it is. We are looking for this grain of sand in a box of sand that is 2 meters each side. This is for modern sample, and if we go to this 50 to Neanderthal, this is this huge. So it's the whole sophistication here, the physics sophistication is very, very important. And this is the physics sophistication. Just, you know, it's going fast, but we start from this place where we would put our target sample that is ready to measurement. And then it will be spattered by cesium ions so that we get rid of nitrogen. I think this is important thing that we know nitrogen is everywhere. Nitrogen has mass 14, like radiocarbon. So if we counted atoms at the end with nitrogen, it would be impossible to detect this very small amount of C14. That's why AMS was only possible when people realized this fact, that cesium ions will create a negative beam that nitrogen is filtered out. And then through the masses, magnetic field here and there will be purification. Let's do it quick. We purify our beam. Also here is a special filter. And at the end, we would separate masses C14, C13, and C12 in separate places. They will bend here differently. That's why this is mass spectrometry. It gives different bending to different masses. We are able to count the masses, the atoms here. And even nowadays, we are able to measure very small samples. And this is important for dating mortar because sometimes we would have not enough for such a large sample of half a milligram or 1 milligram of carbon. So this ion source that allows analysis on gas is some new, maybe 20 years ago, people started to do that in Oxford, and then it spread to old continent, back and forth. So that is everything what I said actually before. Just to summarize what's happening from the start, if we have the sample, we would purify it in a lab and then count. Old days, conventional counting of particles, but mostly what I do, I never worked with conventional methods. Those are still working and useful. But if we're going to cultural heritage, archaeology, it's mostly very small samples that we do, and then AMS is our solution that we need. And then the calculation of ages, I will also talk about the calibration of radiocarbon ages, is our second most important part after preparation and the analysis. So this shortcut shows us what's happening with the sample. We arriving into this point about the calibration. I will hopefully have time to explain why we need the calibration. We have our analysis here, and we measure the concentration of radiocarbon, what I was underlying, C14 over C12. That's what we measure, the ratio. It's always standardized. We compare this to our known samples. We correct for backgrounds. And this number can be translated to radiocarbon age, or translated, we calculate radiocarbon age as Libby gave us this prescription. But is radiocarbon age the real age? Nowadays, we really know and accept this fact that it's not like that. We have to take our numbers from the machine and calibrate it. This calibration, I have two boxes for calibration because as most of us, we know that there may be calibration, standard calibration of conventional radiocarbon ages, which are higher than 0, positive ages. That means things which are old. But now and then, and you will observe also in my presentation, but in your data, if you did some radiocarbon dating, you might end up with negative radiocarbon ages. Those are with C14 that is not really natural. It's the C14 that was created after 1950s that we talk about this as a bomb peak C14. I have this slide again with the cow, but the slide also explains why I underline this need for calibration. There is different factors that are pressing on this bubble of C14 in the atmosphere and reflecting on the starting concentration that we need to put into our equation. Libby and any method has to make this assumption. We have A0 always known and constant, but you can see here that this complicated picture doesn't support constant A0. A0 is changing over time, and those are the main factors. There's a production of C14 in the atmosphere. It's not constant. It is controlled by strength of the geomagnetic field around the Earth. We have geomagnetic field that protects us from cosmic rays, but we have also solar activity, which adds to this protection. So stronger solar activity, we will have stronger protection around the Earth, less C14 produced during such time. And then we have the ocean. I pointed out before, the ocean is a huge carbon reservoir. It's about 70 times of size that we have carbon in biosphere or in the atmosphere. So this 70 times, that's a lot of carbon. Also, the ocean is a huge reservoir where if we have exchange of molecules, say around here, around Greenland, then those molecules need time to go around and they get old. This what is happening, that old water masses, especially around Antarctic, they will be old. They up to 2,500 years old. So such old water masses, when they come up, and there are those upwelling regions, we will have older atmosphere. So that's the impact of the ocean. And it is, of course, also complex a system connected to climate change and nowadays also anthropogenic activities, because we have here in the atmosphere not only burning of fossil carbon that we have after industrial revolution, we have also the nuclear tests that human race put into action after the Second World War. So that complex picture pushes us to this need for calibration. The radiocarbon age, as we calculate from our measurements, it's not a real age, it's just a number that we measure in our samples. And then to translate this to time, we have to forget Libby's model and we have to calibrate the radiocarbon ages. And how do we do that? Fortunately, we have an old sister dendrochronology that allows us to have independent time scale on tree rings. And tree rings allow building long and quite long chronologies back to 13,000 years. We have chronology, dendrochronology that combined with radiocarbon dating gives us so-called calibration curve. This is the whole 50,000. You can see here, tree rings is only back to 13,000. Below that, beyond that, we have other methods that I don't have time to talk about them, but they give us not such a great resolution as tree rings, but still they give us information. How was the radiocarbon age? This is the radiocarbon age here, and the blue curve is the radiocarbon calibration curve. The red one is telling us how the C14 in the atmosphere was changing. If it was not changing, would be a zero line here, or the calibration curve would be just this dashed line, straight line there. So you see the complexity, and you can see, oh, okay, I have this, not by mistake, but just to show you how records, tree rings, and lake sediments, and here's paleothems. This is the records that were used also for building the calibration curve that we're currently using. All right, I didn't remove this one, and now I have to say a few words, because this is, so to speak, the additional detail that we only, it was discovered by this Japanese woman, Miyake. She, as a PhD student, measured a lot of tree rings. You can see here. Each of the point is the tree ring measurement. And she could discover that there was this few years that it was like a jump in radiocarbon activity. We call those now Miyake events. And you can see here, there is 1775, very much of interest to medieval archaeology. Also this 994, that is similar useful tool that it can be used for very precise radiocarbon dating. So those details we still don't have a reconstruction for the whole 13,000 years, and maybe it will come in the future. We will find out about those events more. This is something that radiocarbon community is quite excited about it over the last 10 years or so. But it is an additional detail to this complication of the whole calibration curve. And what I want to point out is this, maybe the age here, Hallstatt Plateau is like a Paradebeispiel, as we say in Swiss German, that for the complication of the plateau radiocarbon ages. But it's not only there. We will see later that also medieval archaeology is affected by this and plagued by the lack of, I call it losing precision at the plateau of radiocarbon ages. You can see here radiocarbon ages, calibration curve, this blue, and there is this time, 2500, where we have continuous, we have like kind of time stopped. That's what I like to say. I liked living on a radiocarbon plateau because you have the impression nothing changes, right? This is something that results in quite long interval as our answer. Our precision on a radiocarbon measurement here shown as a bell curve, red bell curve, is our very precise radiocarbon measurement, is then translated to this very white interval plus minus, say, 100 years in calendar time. So we are losing the precision here, whereas just a few decades older sample returns the precision comparable with our radiocarbon measurements. That is, so to speak, sheer luck in your record, that you might have quite precise calendar age or just this long interval. So yeah, that is what can we do. Yesterday in Bern we had the workshop on Bayesian modeling. That is a combination of radiocarbon with knowledge that you have usually from your excavations, from your studies, if you can put together phases of, if I don't know my language if it's right, phases, archaeological phases for your stands, for your sites, whatever you discover, and you have radiocarbon ages there. If you can put them together and create a model, you might win some precision on calendar ages. But if there is just one sample, as we quite often have, for example, I have here the example. All right, okay, this is what I wanted to show, that there are so many places that you need to do this Bayesian modeling, or the calibration will be complicated in these regions of the plateaus, or double kind of wiggles that we have in the calibration curve. There is no way to go around them except, as I said, Bayesian modeling, or maybe sometime higher precision. Here I have this for art studies, where people come with paintings, old masters paintings, where they quite often they want to see Da Vinci or Rubens or whatever, and they really want precise calendar ages. And when I talk about the sampling, I always ask, what year would you target, and does it make sense at all to do radiocarbon dating? Because if you look here, only this part makes sense to do radiocarbon dating on a painting, or even some other objects. Going down here, we are losing the precision in this region. And in such situation, we really need the Bayesian modeling, tree rings, or information about phases that we need to combine into the model. And of course, the bomb peak is something that we quite often use for the forgeries detection. That's why it's shown here. But there are also cases where, and I have this document from Switzerland that is a Swiss federal charter celebrated in a museum in Schwyz, that it was dated in 1991. It was a part of celebration, but also discussion with historian. Sablonier was the historian who questioned the authenticity of this document. Not that he didn't say that it was written like 100 years ago. He said maybe it was not written in the year that is set somewhere in here. He was suggesting it was written some decades later. You can see here we were really, at that time, we were measuring quite precise. We combined many measurements, and still this precision there gave us double answer. And in a way, the historian here was kind of, with his argument, he was happy. He said, well, radiocarbon tells us there is still the option that they wrote that document later. But I kept a bit of the sample, like remains, that we didn't use up 30 years ago, and we repeated the measurement the result was in agreement with previous dating, but when combined, all of it results in much more precise radiocarbon age. And here, in this very specific case, the higher precision helps us to obtain the better precision for calendar age. So yeah, there are cases where we can improve the precision of radiocarbon ages, and this helps us to improve the precision of calendar ages. So talking about the precision is already assuming that what we measured is really the material from the time that is of our interest. So that we're measuring really a bit of canvas that belongs to the specific painting, and we believe it's all perfectly done. That is the question of accuracy of radiocarbon dating. Accuracy is the ability of our measurements to reproduce the true age of the sample. And here I talk about sample pretreatment a little bit. This comes down to the accuracy. If we have the sample submitted to our lab, we want to remove the contamination that is attached to the sample so that we can tease out the carbon that was fixed in this sample at the time the object was created. In this case, let's say this is this Bundesbrief, and we know that when people produce parchment, they use carbonates, they use all kinds of chemistry. We have to remove this chemistry, and at the end, we just need this proteinous material from the skin of the animal. So we would use basic chemistry, acid, base, to remove carbonates, to remove organic carbon from humic contaminants that we have collected on a sample over the years. And this is just pictures of few samples with the fact that we are losing material in the preparation also, that when planning the measurements, we always have to keep in mind there is substantial amount of material required, still not that much, but we cannot work on invisible samples. That's the fact. And right, I mentioned this is like kind of a basic method in treating organic material, but the next slide will show the complication of conservation. This is something that when talking about archaeological objects, we have to still think sometime there is a conservation that it's intruding into radiocarbon samples, and including additional treatment is kind of requirement that we see this more and more in current preparations of samples. So this step, in the next slide, I show you treatment of wood, that it was the basic treatment with acid base was not sufficient. We had to use solvents, organic solvents, which remove this conservation, and quite often I would say we still think it's not totally sufficient. So that is something that we maybe there is some, I want to show all of them at once. There is something that addresses the issue of accuracy. We have here an object that is medieval banner, textile material and wood where the banner was placed, but also there is a part of this banner that was painted, and we were able to separate part of this contamination, and we were able to measure this contamination, and you can see here, it turns out this is old carbon made of the polymer that was used, was made from oil or from tar, that is absolutely making our samples older. And it's quite possible, as I look at this result, and we have published that, and this discordance of wood with textile, the wood appears much older, for me, much older than the textile. It still points out that this is not an accurate radiocarbon age. And we can see this here. We have nowadays, we used infrared spectroscopy to look at the purity of samples. You can see here the clean wood would be like the red line, and the contamination, which I separated, and this is the result, measurement on this contamination. So you can see this very specific lines point to presence of this polymer. And the blue shows us wood with the paint. So the mix is clearly visible. So that is something that we are increasingly applying in radiocarbon labs to detect potential problems with accuracy of our measurements. How much time do I have? Not so much. Oh, okay. So I wanted to talk about the accuracy of dating bones, because this is what many archaeologists are also struggling with. Bones are not simple material for radiocarbon dating. In a way, we can conclude most of the material is not simple. So, but problematic of dating bones is actually, and this is an example of medieval bones from a location near Zurich, where again, rescue excavations were performed under the school, where they renewed the school, and there were many graves or skeletons found. And the radiocarbon dating, these numbers are not so visible, but also in the next slide, I have just summary of the problem for one of the bones, 75, that appeared to be not consistent in the first set of data. So we would repeat the analysis of this bone many times, and you can see here that most of the bones would agree, they perfectly comparable. The results are in, we say, 2 sigma agreement. That means we can combine them without a problem. Most of them, but 2, which were a little bit older. So from my perspective, these 2 bones were still not properly treated. And I'm quite assured by this number that we have always. Measuring the bones, we would analyze the concentration or amount of carbon and nitrogen, and this is our control number for the purity of the bones. So combining this knowledge that I see disagreement of these 2 bones with the rest, and also comparing the numbers that I have from additional measurements, those being a little bit higher than ideal number that I have usually for the good bone. This is our evaluation of the bones for their accuracy. This maybe just one of the steps how we check the bones for their how good the bones are before we start to prepare them. The preservation of collagen is based on analysis of nitrogen. And this is, again, we do this by combustion of original bone in elemental analyzer, where we measure these elements, how they are in those bones. You can see here that there is a widespread. There are bones that would be quite poor in collagen, and those are mostly not datable. They would result in such problematic values. This quality of collagen, this is also one of the, what was pointed out in a table, that we use this number to evaluate the accuracy of the measurement. All right, so we also would check the quality of the bones with secondary standards. I have this example of a known age bones that we would prepare and measure radiocarbon age just to see, is our method working well for this bone? And definitely here it's quite a good agreement for preparation. I got a bit of the, how this got. I wanted to show few of the problematic charcoals that we date or we evaluate before dating, because actually this is something that we would not date, and explanation is quite simple. We have looking at the material, we would see quite nice looking charcoals, but if we zoom in, you can see here, we have presence of roots. And this is something that is frequently observed in charcoals that are in open sections, plants are growing through. We cannot, nowadays, we don't have a method to remove charcoal, roots from charcoal or wood, and such samples cannot be analyzed. I have the example that pointed to such a problem. Years ago, sample was analyzed without closer evaluations. Maybe my fault, maybe I didn't look under binocular. You can see here a set of data, and this one is quite young, radiocarbon age of maybe 18th century. Later, I was contacted by the student archaeologist, and she said, it seems impossible that this is such a young sample. And we found the material in the archive. You can see here that I was able to look under binocular. I found this root growing there, and we analyzed the root. Is this young? That means this root is not only one root, what it was in a sample. The mix of young roots like this with the really old charcoal, that creates unreliable radiocarbon age. All right, so we have methods to remove roots from sediment, from peat. We would sieve this material through the sieve and then collect fine fraction here. Then this is the material that we can date, but the roots, they are always a wide range of possible contamination. Right, do I have time to speak? Not all of this. Okay, all right, so maybe in 10 minutes, because I was talking about problematic ages of those standard material, bone and charcoal. It's a standard material in radiocarbon dating. And you can see there are problematic cases. Quite often, and I've been doing mortars for 15 years now, people say, oh, this is so difficult, and how does it work? And we agree that it is not straightforward. It's not as simple as burning a bit of wood, but mortars has this beautiful side also, that we can go to sites where there is no organic material in the building, and we try to tease out the time when the building was constructed. And this cartoon made by Scandinavian team, and I believe this is from Åsa Ringholm, who I call her mother of mortar dating. She was archaeologist and art historian in Finland, or she is, and she pushed this method really into modern present day, what we use it, just by combination of her interest in archaeology and art, and also her contacts with physicists in AMS facilities. So burning, how does it work? Burning of the rock, limestone or dolomite, as we will, we also have dolomitic mortars, is the source of quicklime that is then mixed with water and aggregate and put in bit, or some people call it put in between rocks, binds CO2 from the atmosphere. So we have C14 from the atmosphere recorded in those carbonates that are binder in the mortar. And the problems that might occur and occur is that if someone didn't burn the limestone properly, there is still old carbonate in the mortar here. We have to get rid of this. Then there might be, in aggregates, there might be shells from ages, very old shells. Danusia Michalska had such examples. So those are also contamination in here. And actually, those are more problematic than the first case, because we really, I try to separate those, and this is a very special case. But seeing shells, geologists, people who investigate mortars, they can see them. So from the start, we can say there is not much we can do about it. And then there is the other problem of binding CO2 that is like later than the construction time, could be deep late binding or later diagenetic changes that will bring the modern carbon into the binder. Recrystallization right here. So the method that I'm using is similar to the Scandinavian one, maybe just not to go through this complicated machine, but to point out that we are taking the opportunity of different physical and chemical characteristic of binder compared to limestone or dolomite. So we would take a specific fraction of this binder, specific size of grains, and then try to dissolve this carbonate at a different timing. So the anthropogenic, what I call anthropogenic carbonate binder, will dissolve at the fastest, and limestone requires time to dissolve, so it would be somewhere later. And this is, I have a few pictures in the lab. We use this sieving specific grain size, and then the separation is in phosphoric acid in very short time windows of 3 seconds. That's the physically possible time window to do. And then the radiocarbon analysis. So some pictures, we invite people from Czech Republic to come to ETH to see how we do that. If you have time and chance to be in Zurich, you are welcome to see this. There's some, again, pictures from the preparation, and then the CO2 that we trap from those 3 seconds windows, there will be 4 such fractions, and those are, sometimes they are large samples. I would have them graphitized. This is the graphitization system. They are broken in this system and then graphitized. Or we have really small samples, and those will be going directly to the machine, and then the analysis will be performed. I have this example from MODIS studies, and maybe there is not so much time to talk about this, but it's this church in Finland that not only my lab, but a few other labs analyzed the samples, just a comparison between methods. And you can see in a, okay, this is the picture, that's the finished sample that I chose to show here. This is published already ages ago. There were analyses, as I said, people look at the structure of mortar to see what is it promising or is it not. Jan is here, so he can answer those questions, how good mortar samples are. This is absolutely required before we really start doing it. And this figure shows the results from different labs. So you can see here, this is results from Turku. Alf Lindros did this dating, and he provided the sample, also dated by wood. So you see, we know how old this mortar should be, and this is our checkpoint. And you can see here, this is ages that I created from ETH. This church is in Florence, I think, Danusha in Poznań, and then Brussels lab. You can see here we have quite a good agreement between labs. There is results from Milan, a little bit problematic, I would say. Even OSL dating they performed, and yeah, there is this, how should I say, challenge to improve dating of mortar also with other methods. So OSL is one of the options. Right, this is with the calibration. You can see again this historic date based on wood fragments, but also and this agreement between the labs. So yeah, example from Switzerland with Mustayer is one of the sites that Pavla is also has included in her project, and she's working there quite a couple times already. I've done this with Marta Caroselli, and her project was just to do the first dating of dolomitic mortars. And you can see here, we are quite in a range. You can see here from this calibration. We know that this church was built around 775. We have the radiocarbon dating on 3 rings there. So the radiocarbon from the first fraction and second fraction is combined together because we see this agreement between both fractions allows us to do this. We combine this and then calibrate, and our historic dating is really in agreement with our Mustayer at least for this sample. I'm not saying for all the samples, but this is, let's say, huge talk for a discussion of problems in different Mustair samples. Okay, how are we? 13. This is almost the last slide, and kind of something that is not quite frequently discussed at archaeological presentations, because this is the future, as you can see. It's not much about the past. This is the future of radiocarbon, or how a paper written already 10 years ago. The bomb peak I mentioned to you, it was created after 1950, and then it disappeared over the time. It disappeared not because radiocarbon was decaying, but because CO2 was going into the ocean. So it took the activity down to the ocean, but at some point, the fossil fuel combustion, which was going on starting from the mid-18th century, you can see here, if there was no bomb peak, the C14 would be long time ago quite down. So atmosphere became older through this, and is constantly becoming older because we are burning fossil carbon. We're putting extra CO2, and this CO2 has no radiocarbon. It's only old carbon in the CO2. And that creates this artificial aging of the atmosphere. So the future models rely on this, or depend on this, how much of the fossil carbon we are pumping into the atmosphere. Which of the scenarios, as we know, the green one would be our dream, that we stop using fossil carbon for, and then that would be ideal for radiocarbon, because we would be almost at the A0 as the method started. But it seems that the other scenarios are more realistic, and therefore the atmosphere constantly becomes too old. And in the future, and not quite distant future, I would say, because even 2050, 2060, you can see here, in the worst case, we would be also almost in Roman times with the atmosphere. So that's something that, okay, I know archaeologists have other ways to deal with the issues, but let's say rescue excavations with dating charcoal from the site, if they result in some, if they result in radiocarbon ages around 500 years, it won't tell us that those are really samples from medieval times, because they might be also charcoal from the most recent burning of something. So that's in the future. We don't know how it will develop. We have this measurement of the bomb peak is constantly done at different stations around the world. There's one in, I don't know if in Czech Republic, but definitely Jungfrau Joch in Switzerland. They collect samples and measure this C14 signal every second month, or every month there is one point, and then this development is monitored. So we will have the record. What happened in the past is just that the calibration becomes more complicated if we have. And I have this just shown for sites in Switzerland and Hengeberg where we are, or some clean villages, or some places around the world, that just leaves that I collected, or my colleagues collected from different locations. You can see how the effect of fossil combustion is changing the C14 signal locally, dependent how clean the place is. If you are in an environment as clean as this, or if you are in a town like Bangkok, you will have this signal so different from the calibration curve. So I think this is the last, and I don't know if I have to repeat this, how useful the radiocarbon is. I hope I showed a bit that it is useful, that there are those problems with conservation. We need to monitor the purity of the samples, and there are samples that we always have to somehow tease out the problem before we really have the results. It's possible to observe and to measure, to look at the contamination before we do the radiocarbon dating. This is what I call planning of the radiocarbon dating, thinking about the precision, potential contamination, and the requirements also, what the archaeologists have in mind when they want to date something. Maybe sometimes doesn't make sense to date objects which cannot provide us reliable answers. So I talk about this quite a lot, that collaboration with Radiocarbon Lab is the first step to establish, to go for successful radiocarbon dating, because such an exchange helps to pin down the problems before paying the analysis, as many people say, expensive. So yeah, and fossil fuel combustion is something I used to speak only to conservators when they deal with art objects and forgeries, but it's actually something that we all are facing, this complication with the calibration. And I always profit from interdisciplinary collaborations, and I think this goes both ways, that we talk to each other, we have those exchanges, and then I have 60 or 70 slides like archaeologists would. Okay, so that's it. I think, thank you for your attention. This is insight to our lab, and I have this invitation to the conference in Poland, not far away from here, in Jelenia Góra, that facility in Gliwice. There is a radiocarbon lab, quite established, and they organize these conferences every third year. You see, it's quite tradition, older than some young people here. So I think it would be great to see some archaeologists from here. I'm sure it'd be interesting. Okay, thank you. Sorry for taking so much time.